Hey guys, we're going to take a look at our last section here in chapter 5. It's called the substitution rule. We are going to be looking at more difficult functions to find antiderivatives of. So what we've done so far, we've really just stuck to polynomials, maybe seen e to the x once in a while, some simple trig stuff for antiderivatives. We're going to get more advanced. Let's take a look. So 5.5, our textbook calls this the substitution rule. And you know, using the word rule like that, it kind of sounds like product rule or chain rule. It's not what's happening. This is not a formula, it's a technique. And while this book calls it the substitution rule, it's more commonly referred to as U substitution. So I've got that name there at the top. We're going to, turns out we use the variable u to rewrite the function in a form that's much simpler. Okay, let's see it as an example. Let's say we wanted to find the indefinite integral for 2x times x squared plus 1 to the 10th dx. Think, wow, just looking at that, I don't know. You know, maybe one strategy here, since we're raising that to the 10th power, what if we were to multiply out x squared plus 1 by itself 10 times and then distribute the 2x and make it just a massive polynomial? You could do that, but there's a much faster way. And obviously we'll see cases where you couldn't just expand. All right, so what is this U substitution all about? Follow along. We'll kind of see how it plays out, and then we'll kind of look back and see just exactly, you know, kind of how all the pieces fit together. All right. So first thing we're going to do is say, okay, we're going to create this new variable u. We're going to say u equals what is inside those parentheses. I'm going to say u is equal to x squared plus 1. I think, okay, what would that imply for du, right? Thinking of u equals x squared plus 1, what if you were to take the differential of both sides? Why would we do that? Obviously, we're going to see where this goes. So the differential of u is du, okay? On the right side, we take the derivative and then multiply by dx. So 2x times dx. All right. How is this useful? Okay. Take a look at what we have there. Take a look at the integral we're trying to find. And here's where the substitution comes in. So in the integral, the x squared plus 1 is going to become simply u. We'll have u raised to the 10th. And the 2x times dx, right? Everything is being multiplied here, so we could rearrange the order. 2x times dx, both of them together get replaced with simply du. So when we've replaced the x squared plus 1, and when we've replaced the 2x dx, it's going to look much simpler. All we would have is u to the 10th du. Now it's still the same integral because we have this work over here, but there we go. It's just written so much simpler. Now, all we got to do is think, okay, rewriting that as u to the 10th du, is it now simple enough where I could easily take the antiderivative? And yeah, you know, u to the 10th, that antiderivative is 1 over 11 u to the 11th plus c. Just like that. Now, the final answer, we're going to go and we're going to replace the u with the x squared plus 1. So our final answer needs to be in terms of x. 1 over 11 x squared plus 1 to the 11th plus c. And we got it. There's our antiderivative of that original function. Okay, just kind of looking back on it again. Obviously, we're going to do a lot more examples, different varieties. But we said, okay, kind of like that was that key step, right? The setup, the u and the du, and then replacing. And you think, wow, that's, I mean, that's so much, right? That's u. The rest of it together becomes du. Now just think of it as a new question. What is this antiderivative? And then in the very last step, plug what u is equal to back in, and we'll have it. There's other things to mention, but we'll kind of do that as maybe more examples play out. Now, maybe you're looking at this final answer and you're like, really? Like, if I really took the derivative of this, that should give me what I see here, 2x x squared plus 1 to the 10th. We can always check our work here. I think it's a good idea, at least in this first one, to just kind of see how this would go. If we want to check our work, you know, we take a derivative, right? Go the other way. So taking a derivative of 1 over 11, x squared plus 1 to the 11. We don't need to worry about the plus c. We know that derivative is going to be 0. The derivative here requires chain rule, right? We need to multiply the 11 down. Let's think of it this way. This 1/11 is a constant that can carry along. This 11 will multiply down. We'll repeat the x squared plus 1. Now it's to the 10th. And then we'll multiply by the derivative of that x squared plus 1, the 2x. And what happens? Well, the 11s cancel. We could put that 2x in front if we wanted. And now it's 2x times x squared plus 1 to the 10th. That's exactly what we started with. So yes, this answer here was the antiderivative. Okay, it seems like magic. Kind of, you know, there's some questions I know and some other details that I'll talk about. But there you have it. I mean, if we took the derivative and we got it, then it must have worked. What's happening? Notice that we needed a chain rule, right, when we did the derivative to check. U substitution reverses the chain rule. We don't have a reverse process for the product rule or the quotient rule. We do have a reverse process for the chain rule, and it's this. Okay. You know what? I will mention one other thing here. U substitution reverses the chain rule. What did we take as u back here? It was the inside function, right? Think about the chain rule. The outside inside is what makes it challenging. We took our u to be the inside. The du was the derivative of the inside, so that accounted for that part, the 2x in this case, and then it all kind of fell together. Okay, very nice. From here, all we're going to do is practice this in a bunch of examples. That's all the theory. It's now just a matter of putting it into practice in all kinds of different contexts. So we're going to look at these 4 examples. There's actually, after these 4, we're also going to do an example of a definite integral, and that'll look just a little bit different. But obviously, we're going to start with these indefinite integrals, all very different. Notice part A is actually very similar to the one we just did, a little change there, but the rest are going to present us with different scenarios. I'm going to stop this video here. And then we will get to, you know what, let's actually do part A, since it's really similar to the one that we just did. And then we'll pick up the rest. So starting it off. Find the indefinite integral. Part A, we've got x squared plus 1 to the 10th. Just this one being so close, we can do this here as a comparison. Okay, so we'll say, all right. I see what I'm looking at here. I'm going to think reverse chain rule. So what I'll take as u, what's inside those parentheses, right? Still going to be x squared plus 1. Okay. After I pick u, then I need to figure out what du equals, right? And this is the differential. So I'm going to take the derivative there and then multiply by dx. Notice du is still 2x dx. It's still the derivative of x squared plus 1 times dx. There's no 2 up here, but obviously that doesn't influence taking the differential. It's still 2x dx. Okay, now let's think about this. I don't see a 2x in front. All I see is x. Is that a problem? No, I can take that into account. This right here, this is an equation, just like any other equation. I could divide both sides by 2. Let's make this 1/2 du equals x dx. And that'll do it for me. This part here inside becomes u. These two together, x times dx, will become 1/2 du. And so my new integral is u to the 10th times 1/2 du. Okay, and we're looking really good. What to do from here? Okay, there was a property of integrals a few sections back. Any constants like this that are multiplied, we can move out front. I'm going to move that 1/2 to the front of this integral, just to make that a little bit easier for me. Now I've got the u to the 10th. So that antiderivative 1/11 u to the 11 plus c. I can multiply those 1/22 u to the 11 plus c. But my final answer, I'm going to put the u back in 1/22 x squared plus 1 to the 11th plus c. Now we got it. So the fact that that 2 wasn't there, it simply meant I needed to divide that 2 over, and then I can proceed. And the only difference in the final answers is this has a 1/2 factor where the other one did not. Otherwise, it played out the same way. Okay, one thing about dividing a number over, we can only do that with a constant. Variables, we can't go there. We can't move variables across because in the end, we can't have any x's. That's kind of the other thing to mention here about u substitution. When you create your new integral, there cannot be any x's or whatever the original variable was. It has to be all u and du. And then we can proceed like it's a new question almost, right? Okay, very good. Glad we did this one in this video. Let's stop here and then we'll get to some of those other challenging examples.